I'm going to talk you through some of the uses of radiation. I'm going to talk you through their uses based on how penetrating they are, how ionizing they are, and the half-life of the source. Firstly, smoke alarms. Smoke alarms use alpha sources because they're least penetrating. The source used is generally americium-241. The alpha particles complete a circuit. When there is smoke, then the alpha particles are stopped by the smoke particles. This makes the alarm sound. Beta and gamma wouldn't work in this situation because they're too penetrating. Also, it needs to be a charged particle, so gamma wouldn't work because it is not charged. We can measure the thickness of paper to make sure that all paper is exactly the same thickness. We use a beta source. Alpha wouldn't be penetrating enough. It wouldn't get through any paper. Gamma would be too penetrating. It would all go through paper. When the paper is too thick, then less of the beta gets through, so the rollers can be moved closer. If the paper is too thin, then more of the beta gets through, so the rollers are moved apart. In this way, they can constantly adjust the rollers to make sure it's always the same thickness. Tracers are used for two reasons, in medicine and in industry. In medical use, a tracer will be injected. It will usually be a beta source, and beta because it's penetrating enough to leave the body. We would always use a source which has a very short half-life. And an example is technetium-99, which has a half-life of about 6 hours. So this means that the patient is not radioactive for a long time after the treatment. It means that the beta particles can be detected outside the body, so we can do things like analyze blood flow. In industrial uses, it's a similar idea. Let's say, for example, there's a leak in a pipe. Well, we could dig up the entire road and try and find the leak. But instead of doing that, we can inject a gamma source into the flow. The gamma source will leave at the leak in the pipe, and we can move a Geiger-Müller tube along at ground level to find where the leak is. So at the leak there's going to be a lot of radiation, and after the leak there's not going to be a lot of radiation. We use gamma because it's the only one that will actually penetrate the ground. Alpha and beta wouldn't be very useful to us there. Again, we're going to pick something with a short enough half-life to mean that we haven't left the pipework radioactive for a long time. We can use radiation for sterilising, and actually all medical apparatus is sterilised by radioactive sources. The radiation kills any bacteria, and then the equipment is packaged so it's always going to be sterile at use. Now on to uses using half-life. We can date things like rocks or fossil samples with radioactive isotopes. Carbon dating is used for dating organic samples, and uranium dating is used for dating rocks. Carbon-14 has a half-life of about 5,700 years. Carbon-14 is made at a constant rate in our atmosphere, and therefore our organic compounds always have a certain ratio of carbon-14 to carbon-12. So when a bone is made, it has a certain ratio of carbon-14 to carbon-12 in it. As time goes on, the carbon-14 decays, and so there's less carbon-14 but a fixed amount of carbon-12. So by analysing the ratio, we can work out the number of half-lives that have passed, and therefore the age of the sample. Lastly, another medical use for treatment this time is radiotherapy. In radiotherapy, once they've located the tumour, they can move a gamma source around the patient. This means that the gamma rays are focused on the tumour, and so it kills not many healthy cells, but kills many cells in the tumour. Thank you for watching Guerrilla Physics. Please do like, share and subscribe. That really helps me be more useful to more people. Also, please go ahead and check out Guerrilla Chemistry and Guerrilla Biology. You can expect the same sorts of things, past paper questions and videos to help you understand topics. Thanks once again for watching.